So in this section, rather than studying sequences, we will study what are known as series. Can I have an example of a sequence? Thank you. 2, 4, 6, 8. So Mitch has a real nice example of a sequence for us. Well, I'm going to give you a series. Basically, you can turn a sequence into a series by replacing the commas with plus signs. 2 plus 4 plus 6 plus 8 equals what? Well, it equals 20. Okay? Now, let's give you a more interesting sequence. 2, 4, 6, Is it okay if I do this? Who's with me? All right? Beautiful. I'd like to write the corresponding series. Can you give me the series that would match up with that? 2 plus 4 plus 6 plus, is it okay to do this? What's that mean? That means etc. It means the pattern continues, and you can only do it as long as everyone knows what you're talking about. Right? Plus what? 200 equals what? 10,100. Everyone clear? Yeah, how do you know that? That's ridiculous. Is it right? Well, it depends how much trust you have in your instructor at this point. Did I just guess? No, I actually used a trick, and I should show you. I should show you the trick. It's a cool trick. One of the most famous series of all time, in my mind anyways, is this one. And I'll tell you the story I heard, okay? How many of you have ever heard of a mathematician named Gauss? You have? Oh, I mentioned him. Okay. Did I tell you Gauss's story when he was in first grade? Carl Friedrich Gauss, okay, one of the greatest mathematicians of all time. And this is several hundred years ago, okay? He's a troublemaker in school because he was bored to death. I mean, just, you've seen Cameron sometimes, when he has that look. Today he's fine. But sometimes he's just kind of like, man. Today, he's cool. It's a Monday. But sometimes, all right, so Gauss sat behind Cameron, right there next to Abby. And Carl would sit back there and just cause trouble. This is first grade. So the teacher's so mad, teacher says, all right, Carl, I'm giving you a problem to do. You got to add the numbers from 1 to 100, and you may not leave the corner till you do. All right? So he sits there, scratches out a little bit of work, and all of a sudden, about 3 minutes later, he's like, I'm done. 5,050. So, by the way, the fact that I know this story, can anyone tell me how I came up with 10,100? I noticed it was double Carl's favorite. Okay? You guys with me? Now, back to Carl. How did he do it in first grade? Well, here's what he did. It's really clever. By the way, those of you that added this series, 2 plus 4 plus 6 plus 8, and got 20, can you tell me how you did it? That's what I did, too. I remember my dad, he was an engineer. He taught me at a very early age, if you have to add a lot of numbers, it's good to be clever about how you add them. You know, look for tens is what I was told. Okay? So Carl knew this kind of approach, right? And so what he did was he said, well, let me write down the series again, backwards. What would be the last one he'd write down then? 1, right? He'd write 100, 99, 98, and then down to 1. And then he said, well, you know, if I add these, look what happens. Do you see what's happening? We always get 101. Does that make sense to people? How many 101s are there in this little list with the dot, dot, dot right there? There are 100 of them. They're actually labeled by the orange numbers on top. This is equal to 101 times 100. Does that make sense to people? It made sense to Carl. He's in first grade. I know they hadn't covered multiplication yet, but he knew that if you multiply by 100, you don't have to know anything. All you have to do is what? Okay, so it's 101 with a couple zeros after it. But he also knew, oh, wait a minute, I have double what I'm supposed to have, right? So now what's he have to do? Divide by 2. 10,100 divided by 2. What's 10,000 divided by 2? 5,000. What's 100 divided by 2? 50. What's that? Because remember that the teacher gave him the orange problem. He added on the pink problem, and so he actually doubled what he was supposed to find, right? He added the numbers from 100 to 1 to the numbers from 100 to 1. And so he really had twice as much as he was supposed to. Does that make sense? Again, one of the smartest mathematicians of all time. But it's a very cool trick. And you can learn some things about series by studying what he did. Okay? Now, the title of this section is not series, it's summation notation. Okay? And we're gonna come up with a letter from a Greek letter. Do you guys know any Greek? Do you guys know what this means? What letter that is? It means add. That's right. That's what it's going to mean. The reason it does, it's the Greek letter sigma. All right, so this is their capital S. This is capital sigma, and S stands for sum. Okay? So when you see this letter, sigma means sum. We're going to have a sum. And so what I'd like to do is I'd like to show you how to write these examples using summation notation. Okay. So the way I would do this one, Gauss's, I'll start with that. I put a sigma here. And I say that what I'm adding are a bunch of numbers I'm going to call n. That's what our book does. And now I have to tell it where n starts and where n ends. N equals 1 to what? 100. 1 to 100. That make sense? So that's another way of writing Gauss's series. Here, let's try it here. this one, well, I'm not really adding n anymore. What I'm going to say instead, when n goes from 1 to 100, what I'm adding is 2 times n. Does that make sense to you guys? So what's the first term? Well, for the first term, it's 2 times 1. The next term is 2 times 2. The next term is 2 times 3, up to, what's the last term? 2 times 100, and that's the 200. If I wanted to rewrite the example Mitch gave us, okay, how could I do it? Well, I could say that this is the same as the sum. I wouldn't go n equals 1 to 100. I would go n equals 1 to what? No, not 20. 20 was the actual sum of the whole thing. You want to look at the series itself, and you want to say to yourself, well, how many terms are there? Now, there's 4, right? 2, 4, 6, 8. There's going to be 4 terms. N equals 1 to 4, 2 times n. Always take 2 times n. Oh, that's a good question. Let's stay away from that for a minute, okay? Let me put it on the board. Remind me to explain the exclamation point. Well, what number are you looking at? 8? That's for homework. All right, I'll explain it before we go home. Here. Let's try looking at this example. I'm going to write the sum, and you guys write it out the long way. Okay, I'm going to use summation notation. Let's say n equals 1 to 3 of 1 over n plus 1. I'd like to compute what that is. I'll pause while you guys write out the terms and see what you can get. So we're going to write out 3 fractions because we need 1 over 1 plus 1 plus 1 over 2 plus 1 plus 1 over 3 plus 1. The n changes as I go from term to term. That was n. N started at 1 and it ended at 3. Does that make sense to people? That's how summation notation works. You get 1/2 plus 1/3 plus 1/4, which equals, oh, we don't know? All right. I'll help you out. 6/12 plus 4/12 plus 3/12. We need a common denominator of 12, and so I get 13/12. Very nice work. Again, the adding the fractions isn't what is crucial right now. What's crucial now is, do you guys understand how to fill in the numbers? What's that? We better do another one, huh? All right. Let's try. How about this? What's that? That's harder. You want to go the other way. It is on the homework. Let's try this. N equals 4 to 6 of n squared. This is easier, right? We can do this. What's it equal? 4 squared plus, see, I started at 4 because it said n equals 4 is the starting point. Then 5 squared. We're going to stop at 6, it says, right? 6 squared. You stop at the top number. You start at the bottom number, and you stop at the top number. It just means that's where n starts and that's where n ends. And that's one of the reasons I wanted to do this example. Because here's an example where the top number is not the number of terms you have. It's actually just where you stop doing this. Okay? And so I get, what do I get? Let's see. 16 plus 25 plus 36. I'm getting 77. Alex. That's right. Okay. Let me say it this way. If I go back up to the very top of the page, in the book, they write n equals m to k. Whatever this m is, that's the first number I substitute for n. And this is the last number I substitute for n. So back to the question you had, Alex. You were talking about this n equals 1 to 3, this one right here. So we put in a 1 for n, we put in a 2 for n, we put in a 3 for n, and then we stopped because 3 is the last number I put in for n. Okay? Like a foreign language, you know? That's really what this is about. But I can't resist showing you guys one more thing. One more thing. It's one of my favorite pictures in mathematics. Okay? Are you ready? The sum n equals 1 to, what's that mean? Infinity? Well, if you add infinitely many things, it goes on forever, yeah. But if you add a bunch of stuff that goes on forever, well, this is not necessarily true that you're going to get infinity. And that's surprising until you see this example. I think this is really cool. So let's add 1/2 to the nth power. So let's write out the first few terms. What would be the first term? Good. Plus, now when I put in a 2 for n, well, let me really work it out for you so you can see what's happening. Oops, 1/2 to the 3rd power plus 1/2 to the 4th power. And then eventually I can just put ... and you guys understand what's happening, right? So what do we get? 1/2 plus 1/4 plus what? Careful. 1/8, good. Plus, okay. And if I put plus ... are you okay with that? Okay. Now, when you get to a calculus class, we're going to write this equal sign. And we're going to ask you guys, what would it equal if you added all the fractions, meaning forever? And the answer is 1. And you might say, well, why? And I get the answer from my peanut butter and jelly sandwich I had in my lunch every day growing up. So when your mom cut your peanut butter and jelly sandwich, did your mom cut your peanut butter and jelly? Come on, when you're real little. How many people had to cut diagonally? You have a chef for a mother? My mom cut it rectangle-wise. For me, a half sandwich was this. How many had a half sandwich like that? See? And then my grandma wouldn't. She refused to cut the bread. She would fold it. She said it sealed in the flavor. I thought it just made it real squishy. I hated it, but that's what she did. All right? So anyways, my mom would cut it like that. And when I was real little, she would cut it into quarters. Have you ever had that? No? Take a real little kid peanut butter and jelly. There you go. Peanut butter and banana is better. But, okay. So I can use this picture to represent our series. How much of the sandwich have I eaten so far? A half. Plus a fourth. Now, if my mom had wanted to teach me some calculus, she would have been smart. She would have provided a plastic knife. So in my lunch, I could then cut this one in half. And I would eat how much next? Another 8. You guys follow? And then I'd take my knife, a 16th. Imagine you did that forever. What would happen? Would you ever actually eat the whole sandwich? Well, eventually your knife would kind of smush that crumb and you couldn't do it anymore, right? But if you could do it forever, how many sandwiches would you eat? 1. Isn't that weird? This is an example. Oh, this is an example of a certain kind of series. Now, wait a minute. You guys learned about certain kinds of sequences. What are the 2 important kinds of sequences you guys have learned about? Arithmetic and geometric. There are 3 very important series. All right? Arithmetic series, geometric series, and world series. That's best of 7. All right, but anyways, the math series are arithmetic, geometric. Which one do you guys think this is? Why geometric? You're right. This is a geometric series. Why? What's the common ratio that you always multiply by to get the next term? No. To get from one of these to the next one, we keep multiplying by a half. So this is a geometric series where r equals 1/2. Okay? Now I'll say one more thing about the homework. Okay? Well, 2 more things. Because I was asked. Barbara asked me, what's this mean? All right? So I remember being a little kid and learning about this. This is really a cool number. If I take the number 4 and put an exclamation point after it, does anyone know how you read that? 4! I think I'm on a golf course. Right? No. This is called 4 factorial. Abby? That's what it means. 4 times 3 times 2 times 1, which is 24. What's 3 factorial? 3 times 2 times 1, which is 6. What's 2 factorial? 2. What's 1 factorial? What's 0 factorial? Well, defined to be 1. I don't have a good reason right now for you. I do have good reasons, but not right now. Okay? Let's just say that these numbers get very big very quickly. Okay? And these are used in probability, statistics, etc. Many other uses. We may come to some of them next time. We'll see. Oh, that was one of the 2 things. The other thing about the homework. There are nice formulas available for the sum of an arithmetic or geometric series. Okay? You are not responsible for memorizing any of those formulas, but on the homework I'm asking you to use them. For example, Gauss's formula, the sum n equals 1, well, let me say k, to k of the n's, is given by k times k plus 1 over 2. And so in the Gauss example, that's where he got his 5,050. If Gauss had had your book with the formula in it, he could have done even faster. Okay? That's the kind of thing you guys will be doing tonight. Guys, in 24, and this is section 9.2, they want me to use a formula to find the sum. And the sum that they write down is 4 plus 2 plus 0 minus 2 minus ... minus 146. I'll tell you what, let's suppose this was a final exam question. It could be a tough one. But if I gave this as a final exam question, I would do what I usually do. I'd give you some A, B, C kind of stuff, you know? And you know what I'd ask in part A? You don't? Oh, by now you'd know what I would ask. Yeah, that's what I'd say. Is this arithmetic, geometric, or neither? All right? Talk to your neighbor about that while I pause for 15 seconds. What do we say? This is arithmetic. Why? Well, because to get from one term to the next, what am I always doing? I'm always subtracting 2. Does that make sense to people? Okay? So I have an arithmetic sequence. And so if I want to use equation 9.2 to come up with the sum, well, there it is. The sum of the first n terms of an arithmetic sequence, a sub k equals a plus k minus 1d for k greater than or equal to 1 is, well, this is kind of a crazy formula, and so you may need some help using it. That doesn't surprise me, okay? But I'm telling you, the sum is given by either n times a1 plus an over 2, in other words, n times the average, or by this formula. I'm going to use this first one in the middle because I think this makes more sense to me. Let me say it again. A couple days ago, I gave you an example, I guess yesterday, of an arithmetic sequence, although we didn't have a name for it yet. Let me show it to you again. Remember this one? 2 plus 4 plus 6 plus 8 over here on the right side. And I said, how do you add it? We look at the 2 and the 8, and we look at the 4 and the 6. Remember how we did that? Well, another way we could have done it is we could have said, well, let's add the 2 and the 8. All right? And then we'll just times it by n over 2. What's n in this example? What's n in this example? Well, n is 4. There are 4 terms. I should have said what n means. N is the number of terms in your sequence. Okay? So when I say there are n terms, in this example there are 4 terms. What I'm saying is take n divided by 2, and you get 2. And notice that 2 times 10 is the answer. Would that work here? Let's see. Here's an example we did. We added up the numbers from 2 to 200. What is n in this example? N is the number of terms. In this example, n equals what? How many terms are there? Aren't there 100? Right? If you're counting by twos and you go from 2 to 200, aren't there 100 terms? Right? So what I'm saying, according to my formula, is that the sum is equal to 100 times the average. The average of what? Well, 2 plus 200. The first term plus the last term divided by 2. And so it really is 100 times, and what's 202 divided by 2? That'd be 101. It really does give you that 10,100. Because, again, take the first and last term. Right in the middle there would be the average. Okay? So instead of adding 2 and 200 and 4 and 198, you could just add 101 100 times, and you'll get the exact same sum. I don't know if you understand the formula. I'm trying. But for the sake of time, it is time to move on and just show you how it works. So here I go. S equals n times a1 plus an over 2. Again, n is the number of terms, and this is what I would call the average value. In the last example, the average value was 101, because when I took 2 and 200, halfway in between there was 101. In this example, oh, here's a tough thing. What is n? How many terms are there? Well, I guess it would help if I would try to write this with sigma notation. See, when you use sigma notation, what you might do is you might say k equals 1 to n a sub k. All right? And so let's see how this would work. In this example, it's going to be k equals 1 to n. And what I'll do is I'll write it as I would write it this way. 4 minus 2 times k minus 1. That's not going to help you guys. That's not going to help you guys. I think what you have to do, a better approach maybe, is just to count them, okay, for us. Count the number of terms, okay? If I asked you, are there 146 terms, would you say that's the right answer, too many or too few? That's way too many, right? So then what I might say is well, let's chop that in half, because we're going down 2 every time. Does that make sense? So maybe I think 73, is that the right answer? Too many or not enough? Okay, because 73 would be the right answer if you started here. But I also have to add on this one, and this one. So I'm getting 76 for n. Abby, you had a question. Thanks for being patient. Okay. So I'm getting that n is 76. Now, the average value, well, I can actually fill those in because I have the first term, which is 4. I have the last term, which is negative 146 over 2. So the average value is going to be negative. I can see that. 76 times, let's see, that's negative 142 over 2 is negative 71. And so if you can do 76 times 71, put a negative sign in front, you should get it. Does that give me the answer? Negative, what's it say, 4... 24. Negative 5,396.